Okay, good morning, good afternoon, good evening, everyone. Welcome to our first webinar on what's new in MPEG after the 131st MPEG meeting that has concluded on 3rd of July 2020. My name is Christian Timmerer and I will be the moderator of this session where we have a set of topics and presenters prepared, starting with an introduction by Jörn Ostermann, who will present very soon. And we will immediately start with Jörn's intro. If you have questions, please go to Slido. I will post the link in the chat from time to time. Please feel free to go there, ask questions. Please upvote the questions. We will take them in a moderated way at the end of all the presentations. And now I would appreciate if Jörn, you could give your brief welcome and introduction.
Yes, thank you, Christian. Good afternoon, good evening, good morning. Yes, after 130 MPEG meetings, the founder of MPEG, Jörn, retired, and we had our first MPEG meeting without him at the beginning of this month. And we think it is good to tell you that MPEG is thriving, that MPEG will work and will continue. And the purpose of this hour is to show you what were the results of the last meeting. So we will have a report on versatile video coding, our flagship project in video coding, basically the best video codec that we think is available now, almost 10 years after we published HEVC. Audio, we will have a presentation on the new audio profile, which tells you that MPEG is actually reacting fast to industry demands. Video was there. In addition to that, well, there is point clouds as the next important visual media. We have a regional report on this. Point clouds are part of immersive video, immersive entertainment. And we will also report about the achievements in this area of immersive video. And finally, a codec is not everything you need. You need also systems to store, to transport, to stream the data. So we will also report on MPEG systems, which tells you on what we do in order to support these new codecs. And I guess I stop here and back to you, Christian.
Thank you. And I would like to invite Gary now to share his screen to give us an overview about versatile video coding.
Okay, I think my screen should be visible now.
Yes, but not in presentation mode. Maybe you.
Yes, I'm having trouble switching to, let's see here, maybe this, no, that's not doing it either. All right,
Yes,
is that better?
Very good. Yes, very good, thank you.
The Zoom keeps wanting to put something else on top. Okay, that works. This was a big meeting for the video community. We in JVET, the Joint Video Experts team of I2T and ISO and IEC, achieved a huge milestone at this meeting in the finalization of versatile video coding known as VVC. This is the kind of milestone that comes along roughly once every decade, although we did it faster this time. This is the completion of the next major generation of standards in I2T and ISO and IEC, completed at the most recent MPEG meeting. Jens Reiner Ohm and I are the co-chairs of the JVET, and we prepared this slide deck together. versatile video coding in I2T. It's known as H.266. And that has the core coding tools in it, the Bitstream syntax and so forth. We also are finalizing at the same meeting something called versatile SEI messages for coded video bitstreams. Traditionally, we have had something called SEI messages that we can send along with video content, and we have generally specified that within a video coding spec. This time we're making a separate standalone spec that could be applied in different contexts and issuing that as its own standard. So that's what VSEI is. And then, of course, we have software implementation, encoder description, and we're working on verification testing and conformance. But this is the big milestone for finishing VVC at this meeting. As a rough characterization of its performance, we have a chart here, especially for high resolution video coding. It's a major advance in compression capability. The classes A1 and A2 are shown here with PSNR based results for the random access configuration, which is the most important, generally considered important use case, and with camera captured content. You see the two first rows are two different types of 4K resolution, Ultra HD, and we're getting above 40% improvement in compression capability. So you should be able to compress, well, in PSNR terms, at least 40% and still get the same visual quality relative to the HEVC standard that was standardized, I think, 7 years ago. So this is a big step forward. The decoder complexity is somewhat less than double that of HEVC, so it's quite practical to implement. The encoder complexity, there's a lot of flexibility there of how complex an encoder you want to make, but there is a substantial increase in encoder complexity associated with getting the improvement in coding efficiency, and but it's still quite practical, and I think commensurate with what has been typical in the past. We also test on various other types of content, such as screen content and so forth. Not all of that is shown here, but the most important cases are sort of the leftmost column, say the top few rows of the leftmost column, where we're getting 35 to 40 or so % in PSNR terms. But the important thing is subjective quality. And what we have found is that we think subjective quality is giving us even better results than the PSNR distortion measure. By the way, there are other distortion measures, and they tend to be showing similar results to PSNR. But we've done some preliminary subjective comparisons, and we seem like we're seeing even more gain in subjective quality than we are in PSNR. So generally, roughly speaking, we think we're getting about a 2-to-1 compression gain over HEVC, which is the previous major standard. And if you go back to AVC, which is the standard most used today for video coding, it's about a 4-to-1 gain over AVC. So this is a huge gain in coding efficiency, but it's not all about coding efficiency. The reason we put versatility in the title of the standard is that it is designed for a wider application scope and a wider range of different types of usage and different types of video content than ever before. It's very good for what we call screen content, things that are computer generated or mixtures of camera and computer generated content. The emphasis is on 10-bit video, but it also supports higher bit depths and lower bit depths if you want to use it that way. Unlike in previous standards where we did several things later as extensions, we have supported a lot in the first version of this standard, including 444 content and say 10-bit and so forth, which have not always been in prior standards. Scalability, multi-view, and we have special provisions for 360-degree video with projection mapping. And it's been tested with point cloud compression. So there's a huge amount, and even we have lossless coding capability built into the standard. So there's a huge amount of different types of video that this can apply to. And there are also quite a few features within the design that are customized for some of these things. We have something called sub-pictures, which has not been used in previous designs. It also has tiles and wave fronts, different kinds of segmentation for parallelism, and but here we're supporting an extraction and merging of sub-bit streams at the bitstream level. So you could take part of one picture and mix it with part of some other picture, or extract a rectangle from coded video content and use that as a separate coded video bitstream all by itself. This can even be done using just file format track information with remapping of where things go in very flexible ways. It has special boundary handling in it for things like 360 video and gradual refresh. Layered scalability is supported in version 1, unlike in prior designs. Also something called reference picture resampling, which lets you adapt the picture resolution predictively relative to previous pictures. It should be good for adaptive streaming and real-time conferencing. Various other high-level syntax features, which I won't go into in further detail. There are, of course, the core coding design. The compression capability comes from a number of new coding tools and features in those coding tools. There are lots and lots of new techniques that have been developed and put into the design for this purpose. Some of that is intra-picture prediction, so you could even apply this to coding an individual picture without using inter-picture prediction. And then we have lots of new inter-prediction tools. Some of the most interesting are like the affine model and decoder side motion refinement is quite interesting. It puts something like a motion search into the decoding process. And like the affine model puts a sort of stretching and warping into the decoding process. We have lots of new adaptivity features and various improvements basically throughout the coding design. And then the bottom item here is there are special support for screen content coding that again is in version 1 of this standard, not being something that we tack on later as an extension. So the version 1 package, unlike what was done in HEVC, version 1 is capable of very good screen content coding. There's obviously a lot more information available between JVET and the JCTVC joint teams. There are more than 10,000 documents that can be studied, and these things are all public. We also have publicly available software that people can experiment with, and of course we encourage experimentation on your own. In further work, we're working more to improve the reference software, develop conformance testing to make sure that implementations conform to the standard. And we're also doing verification testing. So for different types of video content and different applications, we're going to test the subjective gain over prior standards. Overall, this is a big milestone, as I said, in terms of being another major generation of jointly developed standard. It's a big spec that has a lot in it, but we think it's practical and now ready for use. Thank you. That's my presentation.
Thank you, Gary. And we move on to audio presented by Schuyler. Schuyler, please start sharing your screen.
Okay. Okay, where did that go? There it is. Okay, is that, do I got that right? Did I share my screen? Did you get it?
No, not yet.
Okay, now, right?
Now it's here. Thank you.
Very good. Okay, so I want to talk about the work that happened in the most recent MPEG meeting, July, which is about 3D audio baseline profile. And I'll talk what is that new profile and what is the performance of that new profile. MPEG-H 3D audio was a standard that was developed in 2015, and it has a low complexity profile. This supports channels and objects and also higher order ambisonics, which is all the signal types that can be processed by the 3D audio coding toolbox. In particular, audio objects are key components that enable personalization, options, and broadcast applications. For example, when dialogue is one or more audio objects, the volume level of the objects can be adjusted at the decoder side by the user such that the balance of dialogue relative to music and effects can be adjusted, as in, yes, now I can finally hear the dialogue. Furthermore, if dialogue is multilingual, then that's just enabling or disabling certain objects in the mix of objects that are transmitted. So objects provide lots of flexibility, and that's in the baseline standard. In this past meeting, we finalized an amendment which specifies a new profile, which is the baseline profile. So the history of that is a year ago, industry requested a new profile dedicated to broadcast streaming and particularly streaming of immersive music. MPEG heard that request and a year later finalized an amendment which specifies a profile particularly tailored to those applications. This is Amendment 2, and the new profile is the baseline profile. What is the baseline profile is shown here. As I said, it's particularly appropriate for broadcast streaming and high quality immersive music delivery. So we have the low complexity profile shown in this paler green box, and the baseline profile, which is in the darker green box. And we see that the baseline profile is fully a subset of low complexity. The baseline profile supports channels and objects. I mentioned before, low complexity is channels, objects, and HOA. So baseline does not support HOA. It's a subset in that it doesn't have all the tools. So It doesn't support HOA, but it doesn't have the linear prediction toolbox items. It's focused only on high quality and higher rate delivery applications. And it supports many advanced broadcast and streaming features. So for example, it does retain in the low complexity profile loudness control and dynamic range control, which is two tools that are really important for streaming. So DRC is the kind of thing where you can make an adjustment if you're listening to your smartphone on the bus and you want to raise the level of the lowest sounds in the streaming music. That's great, and DRC lets you do that. Rich metadata lets you know what objects are dialogue, English, French, German, and lets you select the language and also adjust the dialogue level. And in addition, it supports these trimming metadata such that a fraction of a packet can be retained so that the audio sample trim spot is exactly aligned with the video frame instant. And this is important for accurate AV splicing such that ads can be inserted, for example, over the top, and we can conceivably insert personalized ad content for each individual. So all these tools are in the baseline profile, giving us a rich and modern music delivery system or audiovisual delivery system. So in addition, as I mentioned before, it has objects, but in particular, it can support up to 24 audio objects in the so-called level 3 of complexity. And this is great for high quality immersive music. So for example, you've got 24 objects that can be placed in the 3-dimensional space around the listener. And this permits a very rich and realistic sound stage. However, it is a subset of low complexity profile, and it is signaled in a backwards compatible fashion such that new low complexity decoders are able to decode this baseline profile stream as well as the low complexity stream. So that way there is a widest as possible interoperability. So that's an overview of what the baseline profile is. Whenever MPEG finishes a spec, or in this case, a profile, it's important to certify and advertise the performance of that profile. And so to do this, at the same meeting, in this past meeting in July, MPEG published as a public document the verification test report on 3D audio baseline profile. So this uses subjective listening. This publishes subjective listening test results on showing the performance of 5 operating points as 5 subjective tests on use cases for this baseline profile. These operating points cover a wide range of bit rates and immersive audio presentations ranging from 12 loudspeakers to headphones. The tests were conducted at 9 test labs worldwide with a total of almost 350 listeners and comprising more than 1 million subjective scores. So a lot of effort went into this test report, and so we can give it a lot of credibility because it has many, many subjects pooled to get the information. And so what is the performance? So we have 5 tests with 5 different operating points, and 2 are pitched at highest rate, highest quality. I'll talk about them in the second bullet item. 3 are tests pitched at medium rates. The 3 with medium rates use the so-called MUSHRA subjective test methodology. This is a 5-point scale, and for all these tests, I can report that they always at or exceeded the excellent scale. So we have technology that's excellent using this Mushra methodology. A first test, labeled test 2, is highly immersive content, 11.1 or 7.1 loudspeakers. So 11.1 would be a 7 horizontal, 4 high, I believe. 7.1 is 5 horizontal, 2 high, ranging from 512 kilobit for the 11.1 and 256 for the 7.1. And again, excellent quality. A second test is slightly less immersive, from 7.1 to the well-known ITUR 5.1 to just stereo at much lower bit rates shown here, also excellent performance. And finally, we use the same highly immersive content as in test 2, but binauralize it for presentation over headphones at an intermediate bit rate, 384, compared to test 2, also with excellent performance. So we're very happy with these tests, which show a wide range of use cases. But I'm very happy to report that 2 tests target ultra high quality. One is a 22 channel presentation at 768 kilobits. And the second is 24 objects. Now I mentioned up front how powerful objects were and how objects really permit a flexible and highly immersive presentation for streaming music. So this is test 5, 24 objects at 1.5 megabits per second, and presented as 11.1, 7 horizontal and 4 high. And for both these tests, the so-called BS1116 methodology is used for the highest quality of subjective assessment. And it scored the so-called ITUR, high quality emissions quality point. It met or exceeded those constraints. And so we've got this baseline technology, which is able to really deliver highest quality in all its use cases. And I think that's a great, great result. So I mentioned that this is requested a year ago, finalized this month. And I would like to report in my last slide that it is already fielded in services. So 360 Reality Audio Music is the name of the service. It's a consortium offering this, and it can be enjoyed from these providers shown here. And we have some URLs down here, and these slides will be available where you can learn more. So the point is, we had a request, we worked hard to make the spec, we worked hard to show the spec had excellent performance, and industry was a partner in that request, and it's already a commercial service. So I think this is a good package and a great story. And that concludes my presentation, and thank you.
Thank you, Schuyler. And we move on to Marius, who will conclude on the first batch of presentations that present about standards that reached FDIS status, that is final draft international status. So that's the final stage of standardization. Before then, the international standard will be produced and published. Marius, the floor is yours.
Yeah, thank you, Christian. Hello, everybody. So I will spend a few minutes in presenting the main highlights from what is called MPEG-I Part 5 with the long name, Visual Volumetric Video-Based Coding and Video-Based Point Cloud Compression. Mainly, I will speak about point cloud compression. And then you will find out at the end of this presentation why we gave such a long name to this part 5. Okay, let me move on. So first of all, what is a point cloud? Actually is like a pixel in a 2D domain, but different in the sense that is already in a 3D space. But there are also some other differences, like the fact that they are not ordered, and there is no relationship between one point and the next one. And each point is defined as a set of coordinates, x, y, z, 3D space, but also attached to these coordinates, we may find attributes like colors, same as pixels, but also other type of attributes like reflectance, transparency, and many other types. Here an example of a point cloud that was captured by several cameras. And yeah, it is presented as a video, but someone can observe some artifacts that are due to the reconstruction process on the legs and on the hair. So indeed, this is not only a video, but a 3D representation. Okay, some other examples that are quite known today, like here the basketball player is represented as a 3D object, and around the background is represented as a video, 360 video, in such a manner that at a certain moment the camera can move around and render from different point views. Same as this other example by Microsoft in one of their HoloLens, when the football players are projected in the physical place and they are represented as 3D objects. One of the problems is that when representing such objects as point clouds with good quality, in a non-compressed form, they are quite big. We are talking about 1 to 3 gigabits per second per object. So just to have simple numbers in head, we are talking about objects like this one here, 800,000 points at about 1 gigabits per second in uncompressed geometry and colors. And it is clear that this representation should be compressed to be useful in applications. So there are some basic principles that we used to create this V-PCC. The one is that we are talking about a space that is very sparse, in the sense that the objects are usually represented by their surface and not by their volume, in such a manner that even if in 3D space, a pixel, a point, has 26 neighbors that can be used for computing prediction and correlations, many of them are transparent, so not useful. We start this work in MPEG in 2014, like any other work done in MPEG, with some exploration at the beginning that made possible to have a call for proposal in 2017. We had several categories. I will not go in the details, but we end up with two solutions, one that is called V-PCC, and is the subject of this press release, and another one that is called G-PCC, and will be probably the subject of the future communication. The point is that V-PCC was promoted as FDIS in July 2020, and the plan is to have G-PCC as FDIS at the end of this year. Okay, what are the main ideas in V-PCC? They're heavily inspired from computer graphics. And one of classic idea in computer graphics is to create the geometry by using information coming from a texture. So the geometry of the object here is creating as a displacement map, and the height of the vertex here is computed by using the intensity of the corresponding pixel in the image. That was one of the idea. And the second one, also very well known in computer graphics, is texture mapping, in the sense that the color of a vertex here on a 3D object is encoded in a pixel in a 2D texture. The main difference is that for V-PCC, we are inversing the operations. How we do that? We consider our object, the 3D object, as a set of points, and we are projecting that object on a plane. What we keep then is the distance from the point to the plane, so the displacement map corresponding to the displacement map, and the color of that vertex will be encoded in a color of a pixel in a 2D domain. You may imagine if we are using one single plane, many points from the point cloud will be projected exactly in the same point of the 2D plane. So therefore, several mechanisms should be developed. And one of these mechanisms is to segment the point cloud in patches. An illustration is provided here from this point cloud. There are several patches that are computed. How the patches are computed is out of the scope of the standard. And then for each patch, we may choose one projection plane that can be either a face of the unitary cube or the diagonal planes of the cube. We did that to be sure that all the operations at the encoder and decoder side, but most important on the decoder side, are maintained in the integer domain. So a patch is then projected on a 2D plane, and therefore we have a bijective relationship between the 3D representation as a set of 3D points, geometry and color, and the 2D representation composed by a map containing the geometry encoded as pixel value, and the other map that is representing the colors, the color on exactly the same position. Of course, it's not as simple as it is, because different situation may occur. And then still, even by doing so, by having segments, it is still possible to have points that are projected in the same 2D position. Therefore, different maps can be created, not only for one single point, but for different points. And here an illustration of such points projected in the same 2D point. The colors and additional attributes are encoded as additional maps. And there is another information which is called occupancy map that is obtained after decoding to indicate which pixel from the 2D maps is used for reconstruction. As an example, the pixels that are encoded here in the black color will not be used for reconstruction, but only the pixels where the patches exist. Additionally, there is a particular type of patch that is called row patch, illustrated here below, that contains all the points that are still badly projected. So it may happen for very complex objects, despite all these additional maps for points to still have missed points, and therefore we encode them in this row patch in such a manner that we have a full bijectivity here. So it is possible to do lossless transformation from this 3D space into a 2D space. Okay, the question may be why we do so. We do so because that representation transformed in 2D maps can be encoded with traditional video codecs, and therefore the problem of having efficient codec for point cloud is solved, because MPEG is very good in video coding. To have some numbers, so we come back to our object. The current implementation that is provided as a reference software, which is, by the way, far from being optimal, as in the video, the reference software is only a starting point, and companies are developing products based on that, but going in much better results than the reference encoders. So we have numbers like the ones indicated here for good quality, high quality even, objects with relatively high motion and a lot of deformations here, up to 7 megabits per second. Objects that are, let's say, less complex in terms of motion and even in terms of cloth deformation can go less. Okay. Yeah, some information is available on mpeg-pcc.org, including publications and also encoder, decoder, software, renderer for Android, Windows, and Linux. One important point is that while creating V-PCC, we realized that the projection-based method for encoding 3D objects or 3D scenes can be also reused for some other purposes. V-PCC was just the first example, but as you will hear today and in other communications, there is another part of MPEG-I, which is called MIV, MPEG Immersive Video, that is a 3D representation, but not a point cloud one, is still a pixel 3D representation, is also projecting that space into a 2D domain and then encode it with classical video codec. These two projects made possible to create something common, which we called visual volumetric video-based coding, which is a framework used by both V-PCC and MIV, and that will also be used for our future projects. And one of these is what we call dynamic mesh coding. And here is the end of my presentation. Thank you, Christian.
Thank you, Marius. And I think it's a perfect transition to move on to the next topic, which is about, as you have mentioned already, MPEG immersive video, or MIV, or MIV, or how you want to pronounce that. And Bart is already to start with this presentation. And this is now a set of presentation that basically gives an overview about standards that just reached committee draft or CD stage, which is the first formal step in the standardization process. And Bart, the floor is yours.
Thank you, Christian. Indeed, I don't have to explain the right side of this slide because Marius has done that for me already. So something that we have decided in the last meeting is that there will be a second edition of the part 5 because that's now at FDIS, and for MIV we also want to be able to make some improvements. And because of this, we have also aligned the timelines. So MIV is going to the committee draft stage at this meeting. That's the reason that I'm allowed to give this presentation. Normally you would have a DIS directly after that. And but we are delaying that by 1 meeting cycle because then we can have a CD for the part 5 second edition next meeting and then DIS meeting after. So that makes more sense. I'm sorry. Yes. So this is an example of MIV test material where you have 15 views. In this case, it's a photorealistic content. Each view is 4K, 2K, 360 degrees omnidirectional, so VR 360 with geometry information. So for every pixel, there is a single depth range value indicating the nearest object. And then there is also a texture attribute. So what happened here is that normally you would call this multi-view plus depth, but we have aligned all our terminology to the 3D graphics standard, basically. So that's why we're now consistently talking about geometry and texture attributes. The other, and on the left, And maybe that's good to point out. So on the right, you can see the constellation of cameras, how they are in space. Maybe the text is a bit small, but that's just an example. And on the left, you can see that this video is rendered from intermediate viewpoints. So this rendering already includes view interpolation. And another example of content is this camera array with 16 physical cameras. In this case, there is specific perspective projection. So MRV is able to handle multiple projections, including the orthographic projection that is used by the point cloud coding. The model of the MRV codec is that you have this multi-view video as input. You encode it into a bitstream, which is an MIV bitstream based on the V-PCC framework. Then there is an MIV decoder renderer, and then the reconstruction is any point within the viewing space. So of course you can reconstruct one of the source views, but you can also reconstruct viewpoints in between. So based on that, it's not a it's a codec plus a renderer. The same for point clouds, of course, where you also have a renderer. Then the intermediate representation, or the coded representation is the atlas, as Marius has already explained. And you can see that in the case of MIV, you often have one or multiple full views, and then some small patches just for the occlusion information that you are missing. So the from the 15 input views, in this case, you can see that only a small amount of information is preserved. And of course, this depends on the sequence and the complexity of the sequence, how much you can reduce. So the bitstream structure is, you have a stream of V-PCC units. First, there's a V-PCC parameter set, which indicates what is coming in the bitstream, so the decoder can know if it can handle the bitstream. And then the V-PCC unit is basically a chunk of data, and then every sub-bit stream is composed of multiple V-PCC units. And then within those V-PCC units, you have access units, which are like the frames, basically. And then there are different types of sub-bit streams. So you have the common atlas data, which is unique to MIV. It carries the view parameters and any infrequent updates you would have. And then you can have multiple atlases, which is also different from point clouds, where you have the geometry video data, the attribute video data, and also the atlas data, which is the patch, the relation between the patch and the source views. The MIV test model has an encoder and a decoder and a renderer. So the encoder model, this is a bit a simplified diagram, but based on the parameters of the source views, there's some automatic parameter selection. Also looking at the first frame to estimate the geometry quality, selecting which views are fully sent and which views are only used to take patches from, and also to set the atlas frame sizes. Then trial view synthesis is used to select redundant, to flag redundant pixels. And then the pixels that are deemed to be relevant are packed into atlases. So then you have the view parameter list, the atlas data, and the video data, which is then still raw, YUV. And this is encoded using a regular video codec. And the test model uses the HEVC test model, so HM 16.16. After that, all these sub-bit streams are multiplexed into a single bit stream, including maybe SCI messages. Then the decoder renderer, it's after decoding all the access unit, you have the geometry upscaling. Then there might be patches that are not visible, or even part of patches that are not visible in the current viewport. So then these can be culled. After that, the Kroon views can be reconstructed, meaning that you have the same representation as the source, except that when a pixel is not available at the decoder, it is not marked to be not used. Then view synthesis is performed. So these blue blocks are the main operations. After that, it might be that there may be some missing pixels, and these are inpainted. And then when the viewport is away from the viewing space as defined in the bitstream, then this can be handled in various ways. And one example that has been implemented is to do a fade. So when you go too far out of the viewing space, then instead of showing artifacts because of missing data, the viewport just fades. So in discussion, it's a flexible standard for multi-view video with depth. It is agnostic to the video codec. We have performed tests using HEVC and VVC. And the MIF main profile is a subset of V3C with some MIV specific extensions. It is possible in principle to extend using more of the features that are available in V3C or even V-PCC, such as using multiple multiple attributes, occlusion video data, SCI messages, and these kind of things. And some MIF specific extensions that I did not discuss for in view of time is to group views or to use auxiliary patches, object-based coding, these kind of things. And yeah, we would like people to participate in this activity, and the test model is publicly available. So it's easy to get started, and I think most test material will be available on request. Thank you.
Thank you, Bart, for this nice overview. And I'd like to hand over to Young-Kwon, who will give an overview about what happened in MPEG system and specifically on the carriage of VVC and EVC.
Okay, thank you, Christian. So let me briefly introduce what has been done in terms of carriage of VVC and EVC in MPEG systems. This is kind of an overview highlight of the systems standard in terms of a carriage of video codec. So there's multiple part of standard involved in a carriage of video coding standard data. So carriage here means in general like storage and delivery of video coding bitstreams in short summary. So whenever there's a kind of video coding standard, mainly there, we need to work on the support or carriage of, that video bitstream over MPEG to TS. So we create amendment to, MPEG to systems. And there's a lot of other things, based on file format, the base specification on the kind of ISO-based media file format. May not be really need to touch it, but for the kind of bitstream using unit structure, we start from 14496-15 MPEG 4/15, which is the kind of defining how to carry unit file formats, based the video bitstreams into the ISO-based media file format. That will be mainly used as a kind of core of carriage of video bitstream into the file, and then there's another part defining the carriage of video data into the file, specialized in kind of image or image sequences. So whenever you want to use the video bitstream as a kind of image, single image or image sequence, you may need to kind of work on this thing. And after that, there are two application formats which will define the brands or kind of interoperability points more specifically for the streaming applications and also kind of image applications. So streaming applications, we use the common media application format CMAF, for defining a brand definition, and also we use MIAF, multi-image application format, to define the interoperability point for image file format specification. In addition to that, you need to define some kind of video codec specific extensions for dash that can goes to 23009-1 part, which is kind of dash part 1 standard. And there's also kind of another transport technology MPEG is working on, which is MPEG Media Transport (MMT), So some additions need to be added to MMT specification for Carriage specific video codec. So these are all the general landscape of Carriage related standard for video coding, and some of them under progress, and some of them are waiting for things ready for dependency relationship. I will give a little bit more detailed update of which activities going on in systems in this phase. Starting from MPEG to systems, so there are two separate amendments are going on in MPEG to systems to carry VVC and EVC respectively. And for the carriage of VVC has reached the second stage called the direct amendment, the DAM, and that will probably reach the final stage in April 2021. So main feature of this part of standard includes the data alignment specification and some of video descriptors to signal how the bitstream is configured and how your decoder needs to be configured whenever you receive the bitstream, and mapping with HRD descriptor and TSTD extension for that is also defined. And there are some constraints on how to carry the elementary stream into the MPEG to TS also defined. And for TSTD extension for VVC case, we are working on the single layer VVC case, and so layered temporal video subset cases. Carriage of VVC is much simpler than that. So it has reached the first milestone CDEM at this meeting, and that means either reach the final stage in July 2021. So main features are generally same, but it's quite simpler than VVC because it doesn't have to carry about it doesn't define the layered case for EVC. So it simply defines the data alignment with pass packet boundary and all the necessary descriptors and constraints, and also TSD, the buffer model extension for EVC. So if you move to the file format area, starting with part 15 extension, there's one amendment to carry including both VVC and EVC carriage. So it has reached the second milestone DAM, and either reached the final milestone by 2021 April. So it has two sections, one related to VVC and another section related to EVC. For VVC case, so basic things to be defined here is, what's a sample for VVC, and what is subsample, so smaller than sample, and what is the sync sample you can start to decode, and how to signal decoder configuration information and so on. And it also supports a single layer case and also a multiple layer case. And when you store multiple layer case, you can store all the layers combined in one track, or you can also do it in a separate tracks. Also, EVC case, it's much simpler than VVC. It only defines a basic minimum definition of sample, subsample, sync sample, and decoder configuration record, etc. And it only currently considers single layer cases for EVC. So as I mentioned that, so we also need to think about using video codec as a single image or image sequences. So another amendment to part 12 of MPEG-H, which is 23008-12 image file format, is ongoing. So it has reached the currently CDEM stage, the first stage, and then it will reach the final milestone by July 2021. It also has two sections. One is VVC related, another one is EVC related. For the VVC related part, it contains all the basic definition of image item, subsample item, And with it also defines the VVC operating points. For the case you need to extract subset out of the Bitstream. Also, it also defines the kind of how to handle sub-picture items as well. It also contains the kind of how to use the image sequences with the VVC, and it defines the two brands for VVC specific cases. One is a VVIC for image and image collections, and another one is a VVCC for image sequences. EVC case, since it doesn't have sub-picture or operating points information, is much simpler than VVC case. So it only has image item definitions and subsample item definitions, but it has defined more precise, brands matched with the kind of EVC profiles. So when you use a baseline profile, then you may have EVC, BI, and BS for image and image sequences. And if you're using main profile, then you could use EVMI and EVMS for image and image sequences. The last thing we've been working on at the previous meeting is the extension of MMT for the carriage of EVC. It has reached the first milestone CDM. It will reach the final milestone in July 2021. Main features in this amendment is to defining what is MPU, which is a kind of the unit is to be transferred by the protocol. Here we define that the MPU for EVC will be compliant CMF track constraint. Okay, that would bring the last page for my presentation. So I'm handing back to Christian.
Thank you very much, Young-Kwon, for this overview about what's going on in MPEG systems and specifically on the carriage of VVC and EVC. And we'd like to conclude this set of presentations with Jörn about the MPEG roadmap.
Thank you, Christian. That was an impressive list of achievements. Thank you very much to everyone presenting that to us. Now, this is a roadmap starting January 2019 up to January 2025. You see there are many arrows over here. These are sort of projects that are finished. We are currently over here. These are the ongoing projects, and it's very normal that in the far future, the density of arrows is not yet as high as we have it in the past. Things will develop. What are the main things that we want to do in the near future? Well, MPEG-I is sort of our vision. We want to have immersive video, which means that we will have extensions to VVC, most likely, to further cater to this aspect of immersive video. As Bart pointed out, immersive video, we are working on it. We want to enable something where you are surrounded by video, but you are also able to walk in the scene. And while you're walking in the scene has to be rendered appropriately. You will have point cloud objects, graphics objects in the scene. You may want to interact with them. The audio, that would be over here, 6 degrees of freedom audio, has to be rendered correctly as you move through the scene. We will also add another media type to this immersive experience. We have audio, video, graphics. Haptics will be part of it. That is sort of in this area of OMAF extensions that we will be working on. That is sort of the grand vision we are looking at. Now, if you look into the details, we are looking at machine learning approaches to video coding. There are two groups looking at it currently that might be changing in the future. One is looking into improving tools within regular video coding within EVC and how they can make use out of neural networks. There's also the concept of end-to-end coding of neural networks that we are looking into. There is video coding for machines. The assumption or fact is today, most video is not looked at least not by humans, just computers are looking at it. So the question is, can we do part of the image analysis at the encoder, transmit these features, and then using these features, different applications can do their work based on these features. And the big question is this approach more efficient than regular video coding? We don't know yet. That's something we are going to find out. We will issue call for evidence pretty soon to this. Now, machine learning is a topic that is all over the place. We are also looking at this from a compression point of view. How do we compress neural networks? If you want to download a neural network, it can take you several hundred megabytes. That's something that you want to do efficiently. And we are working there in the area of neural network compression for multimedia applications. And in the future, we will also work on, and that will be a call for proposals, responses are coming in soon. We will also look at updates to a neural network that you already have on your device. Now, these neural networks are meant for sort of you download them, you update them, let's say once a week, and then you run your application as often as you want. For network-based media processing, where it means you configure algorithms in the cloud to do your media processing, we are working on an update. And for point clouds, which is currently very important for the media industry, but also if you look at LiDAR systems in cars, they are also working with point clouds. We are extending that also to dynamic mesh compression. Now, looking at the green part here, that is basically the system support for all of this. I mean, if you want to have interactive scenes, you can imagine system plays a very important role in this. And if we look at this blue part, this is sort of the first area where MPEG moved out of its core competency, which was audio and video coding. We went into genome compression together with another ISO group, TC276. Why did we do this? Well, MPEG is the place where we know about compression and where we know about quantization. And the first set of standards was ready at the beginning of this year. Now we have a call for proposals out where we look for updates of the technology, and this is sort of the first successful area where we're out of our traditional scope, and I assume we will continue to do that. For example, if you have a factory, Industry 4.0, a lot of data is now coming up. It's temporarily varying, and that will be another area where most likely MPEG will be moving into. Okay, thank you very much. Back to you, Christian.
Thank you, and I will now, and this concludes the presentation.